A food processor appears straightforward: a sturdy base housing a motor, a clear bowl mounted on top, a central shaft rising from the base, interchangeable blades and discs locked in place, a lid that clicks down before the machine will start. It feels like an appliance that could only exist in this arrangement, but its form is the result of layered decisions shaped by human fatigue, mechanical limits, and the physics of rotating mass. Before food processors, food preparation was manual. Chopping herbs meant repeated knife strokes. Grinding meat required hand-cranked grinders that clamped to counters. Slicing vegetables evenly demanded precision and time. Large quantities amplified labor. The limitation was not knowledge of how to cut. It was endurance and consistency. Knives rely on human control. The angle, speed, and force vary with every stroke. For small amounts, this variability is manageable. For large batches, it becomes tiring. The first attempts at mechanized food preparation appeared as hand-cranked choppers and grinders. These devices used rotating blades turned by a handle. They improved efficiency, but still depended on physical effort. The true shift came when electric motors entered the kitchen in the mid-20th century. An electric motor provides consistent rotational speed and torque. But integrating that motor safely into a device that processes wet, solid, and uneven ingredients required careful placement. The most intuitive layout might have been to place the motor above the bowl, directly attached to the blade. But gravity complicates that. If the motor were above the bowl, food particles and moisture could fall into the motor housing. That would introduce contamination and electrical hazard. Placing the motor below the bowl isolates electrical components from food and liquid. The aha moment begins here. The processor's vertical stack is about separation. Food above, motor below, sealed interface in between. The central spindle transmits torque upward through the base into the bowl. This vertical alignment keeps the motor's weight low, stabilizing the appliance during high-speed rotation. Stability is critical. When blades spin at thousands of revolutions per minute, centrifugal force pushes food outward. If the base were lightweight or elevated, vibration could cause the machine to walk across the counter. The heavy base counteracts that force. The bowl shape itself is not arbitrary. It is wide at the top, narrower toward the bottom, with slightly curved walls. This geometry guides ingredients downward and inward toward the blade. When the blade spins, it creates a circular flow. Ingredients are thrown outward by centrifugal force, then slide along the curved walls and fall back toward the center. The bowl is part of the circulation system. If the walls were straight and vertical, food would stick along the edges. If the base were flat, ingredients would escape the blade's path. The curvature ensures recirculation. This is where the realization becomes clearer. The processor does not simply cut food. It moves it repeatedly through the cutting zone. Without continuous recirculation, blades would slice only a small portion of the contents. The blade placement at the bottom maximizes this effect. Gravity pulls ingredients downward into the spinning blades. Each rotation lifts and redistributes pieces. Larger chunks gradually reduce as they repeatedly pass through the cutting path. This is efficient because it uses gravity as an ally. Had the blade been mounted higher in the bowl, ingredients would require forced upward movement to reach it. That would require additional mechanical complexity. Instead, gravity does the work. Trade-offs appear in blade design. The standard S-shaped blade is curved to create both cutting and lifting action. Its angled edges draw food upward slightly before releasing it outward. Too aggressive a blade would pulverize ingredients instantly, generating heat and reducing control. Too passive a blade would fail to chop effectively. Speed selection addresses this balance. Most processors offer multiple speeds or pulse functions. The pulse option allows short bursts, giving users control over texture. Texture is critical. Food preparation is not only about reduction, but about consistency. Overprocessing creates paste. Underprocessing leaves uneven chunks. The lid's locking mechanism introduces another design constraint. A food processor cannot operate with an unsecured lid. The blade is exposed within the bowl. High-speed rotation could eject ingredients dangerously. Thus, safety interlocks became standard. The lid must align precisely with the base, engaging switches that permit operation. This alignment is not cosmetic. It ensures that the mechanical interface between motor shaft and blade is secure before rotation begins. The feed tube involves a different problem. Adding ingredients mid-process should not require stopping the machine entirely. The tube allows gradual insertion while keeping the lid sealed. Its narrow shape prevents hands from reaching the blade. A pusher tool fits snugly inside, guiding food downward. Even this tube's diameter reflects compromise. Wide enough for vegetables, narrow enough for safety. The motor itself must deliver sufficient torque to handle dense ingredients like nuts or dough. High torque demands stronger internal gears and windings, increasing weight and cost. This explains why food processors are heavier than blenders of similar size. Blenders use tall jars and rely on liquid flow to circulate contents. Food processors handle thicker, less fluid mixtures. They require torque over speed. The processor's squat shape reflects this difference. A blender is tall because it relies on vortex formation in liquids. A food processor is wide and shallow because it relies on gravity-driven recirculation in solids. This distinction is subtle but profound. Two appliances solving different fluid dynamics problems require different geometries. Human behavior shaped the final form as well. Kitchen counters have limited space. Appliances must be compact enough to store easily, yet large enough for common batch sizes. The standard bowl capacity reflects typical household needs: large enough for family meals, small enough to lift and wash. Clear plastic bowls became common to allow visual monitoring. Users can see texture changes without opening the lid. Transparency improves control. Cleaning also influenced design. The bowl detaches from the base for washing. Blades are removable. Smooth surfaces minimize trapped food. Sharp internal corners are avoided where possible to prevent buildup. Durability matters too. Repeated blade removal and reattachment must not wear out the spindle. Materials must resist cracking under vibration. The processor exists because it solved a cumulative fatigue problem. Chopping onions for a single meal is manageable. Preparing food for a gathering is not. The appliance centralizes repetitive motion into mechanical rotation. It compresses time. Before processors, large-scale chopping required labor or multiple hands. After processors, one person could accomplish the task quickly. But it is not perfect. It is loud, it occupies space, it requires assembly and cleaning. Yet it persists because its design stabilizes around functional necessity. The motor stays below because gravity and safety demand separation. The bowl remains on top because circulation requires vertical recirculation. The blade stays at the bottom because gravity feeds it continuously. The lid locks because risk must be contained. The shape is not stylistic. It is structural logic made visible. The aha moment often arrives when you recognize that the bowl is not a container. It is a chamber engineered for controlled turbulence. The processor does not just spin blades, it orchestrates movement. Invisible design reveals itself when form aligns perfectly with physics. Food processors look the way they do because they resolve the interplay between torque, gravity, and human workflow. Change one element, raise the motor, flatten the bowl, remove the curve, and performance declines. The design stabilized because it reached equilibrium. When you drop ingredients into the bowl and press the button, you activate a system that converts rotational energy into controlled reduction, a compact device built around vertical force, a motor grounded beneath a transparent chamber. Not flashy, not mysterious, just balanced. And like many mature tools, it becomes invisible once it works. A bowl on top of a motor, quietly solving the physics of preparation, one rotation at a time.